So hello everyone. As you might already see me before, I'm mostly working with simulations. I'm a PhD student of Dr. Loth here in Bratislava, along with my colleagues. If I'm counting correctly, I'm the fourth one today. So let's go into something different today. I'm currently writing something called a rigorous thesis, a minor one, before obtaining my PhD. So I had to decide on a project that is not directly related to what I'm doing for my PhD. And as you may recall, I have written a universal virtual meteor observatory named Asmodeus, which tries to be, just like Felix and Dusan have mentioned, simple and not very complicated simulator. I'm writing something completely different, a very complex and complicated one, because I like toying with computers and models and everything. I'm also helping my colleague Carol with this. However, he's mostly interested in dark flight of meteoroids or meteor dust, and I'm trying to make this really universal from meteoroid through meteor to meteorite all the time. Currently, what we have and what you might have already seen are the flight dynamics equations for ablation luminance, and I'm able to recompute everything for an observer. So in the end, I have usually images like this. I really like this one. And however, it is not very easy to work with an image like this. So usually I apply the bias functions and only select the brightest frame of a meteor and work with this reduced data set. This time we want something different. But we want models. Well, not these kind of models, different kind of models. But if there are any applicants, please feel free to write to me in the chat. Actually, we need to model the Earth, to select an appropriate representation for computation, and to do the same with the atmosphere, find a dynamics model, determine the drag coefficient, and finally solve the equations to obtain a meteor or the brightest frame of one. If all this is met, then maybe, just maybe, we will be able to simulate meteors really well. So they should actually match what is up there. As for the Earth, usually, and when I started my former master's thesis, I was advised to do this as on a model of a flat Earth, which is suitable for local events. So if I have one observer at one point on the Earth, it's possible, or maybe not advisable, but possible to model it as a flat plate and work in the Cartesian coordinate system, where north, east, and up correspond to x, y, and z coordinates, and I can determine the atmospheric density simply as a function of altitude. However, what you get is errors in altitude, which are proportional to the distance or square of the distance over the surface. So it's simple, but not very precise. Naturally, the next extension is to use a spherical Earth, which can already be used for global calculations, which for our system AMOS, which is already going global, as you might have heard, is really suitable. It's still reasonably fast. However, we have to make a choice here. If we are going to work with spherical coordinates, phi, lambda, and r. I think my colleague Carol is doing it like this. It's been described well. However, I don't really like it because the differentials and transform are really non-trivial. However, the advantage is that you can output everything directly. You don't have to care about projections or anything. You just display your data on a chart and it works well for local events as well. For me, however, in a global calculation, it's easier to work in Cartesian coordinates already, where calculations are really straightforward. All the equations can be solved at once. However, I still need to convert them to spherical because I need to obtain r, the distance from the center, or more precisely, the altitude above the surface. So it doesn't really help much. If we're doing this, we can already move to the WGS84 model, the reference ellipsoid. I found a very good new or recent paper by Carl Olsen, which describes a conversion that can be done on a modern CPU very easily. It is fairly complex. However, the code has been already written and tested and proved that it actually does what it promises to do. And I am able to do maybe 500,000 or 1 million conversions per second, which is fast enough even for my huge data sets. So it is a bit of a pain to write this, but when it's done, well, it's really worth using it. Out of these three, I decided in my latest project, or maybe everything I'm ever going to do with meteors, to use this WGS because it just works very well, and the deviation from true geoid shape of the Earth are very negligible, up to 110 meters, if I'm right. And this is a global error. So for local errors, it's even much less. So usually if you have a camera on the surface and a meteor within a few hundred kilometers, it's really not a problem anymore. As for the dynamics, it is a bit worse. However, we may begin with a simple analysis of what we are trying to do. So we have a meteoroid and we have some sort of environment, something that is not directly related to the body. Within the meteoroid, I decided to split the variables I'm using into 3 categories. One of these is the state, which is something that is variable during its lifetime. We begin usually with the position and velocity. However, since our meteors, since I'm not working only with dark flight, they also do ablate. So the mass is changing. And in the more complex models, also the temperature, at least the surface temperature of the body is changing. Or if I'm really to get picky with what I'm doing, it is good to observe or determine the temperature profile across the entire radius of the body as well. And we have a few constants which can be specified or calculated only once for every meteoroid, such as heat capacity, heat of vaporization, density, shape factor, and so on. And although some of them are derived, they can be used during calculations, but I'm not storing them because they have to be recalculated from other of these quantities. As for the environment, we have densities, temperatures, Mach numbers, and so on. So this has to be stored separately from the meteoroid, and only together, finally, we are able to determine the drag coefficient gamma. As for the models, currently I'm experimenting with 3 of them. The first one is, well, sort of a null zero model, which has no ablation. It is still useful for modeling out of the atmosphere. However, for this, we have already many tools which are much better than what I'm going to do here. And we have the basic Zeplecha model, which I'm currently using as a base model, which only accounts for change in mass during the ablation, and some of this mass is converted to energy. I omitted all the equations because they are not very pretty. And finally, what I'm considering to be the state-of-the-art model is by Hill and others in 2005, which has temperature and also accounts for evaporation and latent heat of meteoric material. However, this is still not enough. So currently I'm thinking about it, but I still haven't got to it, to model thermal transport within the body. But still, I shouldn't be going into a full CFD or something like that. So I'm only trying to experiment with linear or something very similar across the radius of the body. However, it starts to get really complicated. As for the atmosphere, Carol is using the International Standard Atmosphere model. I've been experimenting with a very simple isothermal atmosphere where density is just a function of an exponential with a scaled height as its argument. It works, but not very well, especially higher up. The ISA is the international standard, really. So it's used throughout many fields, also in aviation or in rocket science. However, I found out that the model is not very precise up in the thermosphere, which are the altitudes which interested us the most. So we had to move to something even more complex, which is the incoherent scatter model, the models of 90 and 2000. First of all, I thought I'd be using the full model. So if I have the location on the Earth, the time of the day, time of the year, and everything, I would plug it into the model and try to extract the data I'm interested in. However, it turned out to be unbearably slow, especially the web interface, and I wasn't able to download the model. So I'm using the average out snapshot. If I'm modeling the Perseids, I just try to pick up the general location and time and work with this. The last and the most complicated thing here is the atmospheric drag. We have a nice and relatively simple equation of drag. In it, we can obtain the mass and velocity from meteoroid state. 2 more quantities are the density and the shape factor for meteoroids properties. Usually I'm working with spheres because that's everything I know about the particle. And finally, from our atmosphere model, we obtain the density as a function of position. But we still have this damn gamma here. Even if we assume a spherical particle, it's not so easy. Usually, we just set a constant gamma. It's the easy way out. We pick one value. I think this is well agreed upon. And everything is simple, however, not correct, especially high up, it just doesn't work. So the next thing we try to do is to include the Reynolds number. Many people, at least physicists, know that this is the first thing you go to if your calculations in fluid dynamics don't work very well. So you just include your Reynolds number. It's the ratio of inertial to viscous forces, which is pretty easy to calculate. We just plug it in, obtain some value, and based on this value, we have to find some model which just takes into account. The latest one, or the one I found for a spherical particle, this one by Morrison, 2016, is not very simple, but works well. It's not difficult to implement, and it correctly reproduces low Reynolds numbers. So this should limit, in a limit, this should go to the Stokes drag, 24 divided by Reynolds number. And for very high values, it should be approximately constant, which corresponds to a quadratic drag. It also models the drag crisis very well. If you were ever asked why a golf ball has dimples on it, well, this is exactly the reason, because there is a distinct step down in drag coefficient. This model also aims to reproduce this well, so we have obtained much better results. However, it works only down in the atmosphere. So I was very happy. I implemented it. I put in a meteor at 1 milligram at 180 kilometers, and quickly found out its terminal speed was 65 meters per second, which is definitely not correct. So what the hell? What is this? It took me a month, maybe, or not a very intensive study, but still a month, to realize that this model is only useful for incompressible flows, which is definitely not the case. And it certainly doesn't account for very rarefied atmosphere up there, or for shock waves and other effects of supersonic, hypersonic flows. So what we could do next was to incorporate also the Knudsen number, Kn, which is the ratio of mean free path of a particle, or a molecule, and the size of the meteoroid. The definition is fairly easy. It breaks down into 4 roughly defined regions. So if your Knudsen number is very low, you're in continuum, and most equations work pretty well. If it's very high, the flow is free molecular, which can be solved as well. However, in between, it's very complex. So these two models by Loth and Henderson, they start to get pretty complicated. But well, you have computers, so you just punch it in and give it the right numbers, and it works. The last thing we were able to find was the model by Singh and others from MIT. They started from first principles, implemented some advanced simulations in fluid dynamics, and then bridged everything by some empirical functions. So it should work well even high in the atmosphere, in the water, supersonic, hypersonic, slug, everything. I also tried to validate it by simulation. It works. However, I'm not able to do a real validation comparing to some experimental data, but they claim they've done it. So it bridges all these modes that can be encountered. The entire model is on 2 A4 pages, and it also required a very long conversation with the author because I wasn't very sure that the model or the equations they published in the preprint paper were right. But we implemented it. The last thing to choose is an integrator. I've been experimenting with symplectic integrators, however, here, so it's not much of a point. We have to just make a trade-off between speed and accuracy of an integrator. So you have the Euler, the classical one, the Runge-Kutta methods, and Dorman-Prince. The more interesting thing here is that I need to match the frame rate of our Amos cameras. So I need to produce a frame every constant number of milliseconds. So I cannot use an adaptive integrator. Usually they are implemented with various steps, but I need to converge on a finite number of steps after every frame, which means I can only half or double the frames per second. So usually it works like this. Above the atmosphere, we use long steps. Then during the ablation phase, where the mass changes rapidly, we use smaller steps. And then once we are slowed down to several tens of meters per second, we increase the step again, and our results are the best. So to conclude all this, our experimentation shows that for the Earth model, you shouldn't be using the flat Earth at all. It just has too little advantages now that computers are fast enough. But for fast and dirty work, you might use the Spherical Earth. For anything more serious, WGS-84 is the way to go. For the atmosphere, definitely you should be using the RLMSISE model. For large data sets, use one snapshot. For more or high precision work, do it, just export it for the precise time and work with this. With dynamics, I'm very unconvinced that this can be improved very easily by me, but apparently at least Peter Brown's group is doing some very good work. So I'll be getting in touch with you, I hope. For drag, Singh et al. Is the best model, definitely. The author has confirmed it, and comparison to other models are very hopeful for me. For luminosity, again, I think Peter Brown is the way to go, because this model by Hill and others seems to be not very precise. And for integrators, the best compromise between speed and accuracy seems to be the most basic Runge-Kutterford order method. However, if you need to produce many steps, Euler is an acceptable alternative, as long as you don't care about your precision very much. I'm working on a virtual observatory. Not much is here to be shown so far, unfortunately, but I suppose that if you can't click into it, it's not very interesting. I hope to be releasing this on GitHub again, maybe in 2 months, if I'm able to finally conclude this part of the project and move on to my dissertation thesis. However, what I can say, it's really, really fast, an order of magnitude above Python, which has been already optimized by me very thoroughly. So C++ seems to be the way to go if you want speed. And that would be about it. I'm sorry, I used two more minutes than I was okay. So thank you.